we'll stop. And obviously, we have our exam today, so we'll take the exam during lab like normal. All right. So in this chapter here, we started talking about intermolecular forces and a few different types of intermolecular forces. Um, no, I'm sorry, we got to take it today. I think we talked about some intermolecular forces, and those are the forces that basically hold one molecule together with another. So that is three types that we talked about. There was dipole-dipole interaction, and that's the intermolecular force that really is between polar molecules and polar molecules together. And those would be polar molecules that really don't have the ability to hydrogen bond. And that's hydrogen bonding, which is um, another type of dipole-dipole interaction, but it's a relatively strong one. And it is really with polar molecules where there's a hydrogen bonded to a nitrogen, oxygen, or fluorine, allows it to really kind of make a nice sort of bond or a strong bond there. And really, the weakest out of sort of all the few different types of intermolecular forces that we talked about is dispersion forces. And dispersion forces are essentially the forces that hold nonpolar molecules together with nonpolar molecules. All intermolecular forces are essentially the same sort of concept in terms of how they come together. It's basically the opposites attract, so a positive charge, negative charge, attraction to each other. So in a polar molecule, we do have a side that's always positive and a side that's always negative. So they will be attracted to each other. In the hydrogen bonding part, it also is pretty much in a polar molecule where the positive hydrogen is attracted as maybe the negatively charged oxygen, nitrogen, or fluorine that makes that hydrogen bonding possible. And in dispersion forces, those are the ones where we talked about a couple different ways you can sort of get a temporary dipole. And since they are temporary, they don't always have that sort of separation of charge. They are the relatively weakest out of all of them. They can happen from just an instantaneous dipole, and that occurs when all the electrons just sort of move from one side of the molecule to another and temporarily sort of create a positive negative side. You could also induce a dipole by putting a polar molecule or a ion near it, and it will cause that sort of temporary charge separation in your nonpolar molecule, and it gives them a way to basically interact with each other. Now, intermolecular forces are always weaker to intramolecular forces. Intramolecular forces are our things like ionic bonding, covalent bonding within a molecule. Those are always much stronger than those intermolecular forces. Intermolecular forces are responsible for things like boiling point, melting point. So typically, the stronger the intermolecular force, the higher the boiling point, higher the sort of melting point is, because they're together a lot stronger. It takes a lot more energy to basically to break them apart, and obviously that translates to higher boiling points or melting points. So I think where we left off was right about here. So let's just continue on for a bit here and talk about vapor pressure. Vapor pressure is really the tendency of a liquid really to sort of go into the gas phase or be able to sort of go into the gas phase relatively easy. That is what is sometimes referred to as a solution being volatile. It's able to sort of go from the liquid phase into the gas phase relatively easy without a lot of sort of work to do that. And when we do have sort of a liquid in an open container, um, it will completely evaporate off eventually, because when we think about sort of the surface of any liquid, so if we have about the surface of any liquid, we really have two processes occurring. We have evaporation as guys kind of jump out of the liquid part, and then we have condensation basically happening as those guys kind of fall back in. In sort of an open container, what happens is as we sort of do the evaporation process, we also have air, and air will kind of blow some of those guys away, and they are no longer available to basically drop back in. And eventually what will happen is, right, your water level or liquid level will kind of get smaller and smaller as those guys basically evaporate, because the rate of evaporation will kind of increase and the rate of condensation will sort of decrease as well in that sort of process. Also, why when we have, say, a liquid that just spills on the counter or something like that, we have basically that process happening a lot all over the place, you know. And we have obviously air being able to get to all this guys that are coming off. So we kind of move them away. They no longer could come back. And eventually, right, your little kind of puddle there will eventually kind of dry up and kind of go away as a result of that sort of process. Now, because we have this sort of constant process at the surface of the liquid where we have basically those guys jumping into the gas phase, when we do have sort of a liquid in a container, at some point it will reach sort of equilibrium, the rate at which it kind of goes to evaporate and the rate at which it goes through condensation. And as it starts to evaporate, it's obviously going to create a number of sort of gas molecules that are above the liquid. And these gas molecules that are above the liquid obviously are going to cause pressure. And that's what we refer to basically as the vapor pressure of a liquid. And it's a result of obviously gas molecules that have formed above the liquid portion. And obviously they're causing pressure associated with that. So liquids that have really high vapor pressure are said to be volatile. They evaporate really quickly. So really the only way you could kind of get high vapor pressure is if you have a lot of gas molecules that have developed basically above the liquid. In order to get a lot of gas molecules above the liquid, that would imply that you have a good rate of evaporation happening in the liquid to create that to occur. The vapor pressure of a liquid at a given temperature is determined by the intermolecular forces. The larger the intermolecular forces, the lower the vapor pressure would be. And that's sort of the opposite effect here. Obviously, the stronger the intermolecular forces between all the liquid molecules, they're going to hold together for a lot longer, and less of them are going to be able to sort of come up into the gas phase, and we would have less gas molecules above the liquid, and thus we would have a lower vapor pressure in that situation. And that's what we kind of see here in this picture of a container. And this is a liquid in a closed container. Now, in a closed container, what happens is when you put the sort of cap on it, if you will, we do have that rate of evaporation that occurs. So as you can see here, we have a pretty good rate of evaporation. But because it's really in a closed container, it's got pretty much nowhere to go. It can't escape. The air can't really get to it to blow it away or anything like that. So we will start to see these guys start coming back down. And eventually what will happen is we will hit equilibrium. And that means that the rate of evaporation will equal the rate of condensation. And usually what you'll see in sort of a closed container situation, as you can kind of see here, is the liquid level will actually go down a little bit from where it started. So once it reaches that equilibrium, again, you have that sort of increased rate of evaporation to begin with, and some of those guys will come back down into the liquid phase. And usually your liquid in that container will sort of level off a little bit lower than it started with, again, because of that increase in evaporation to begin with. Now, we can actually calculate some of these things using our equation here, the Clausius-Clapeyron Equation, and that's the natural log of the vapor pressure at temperature 1 divided by the vapor pressure at temperature 2 equals delta H. Delta H is, so this is our vapor pressure, both of these at different temperatures. Delta H of vaporization, that's the enthalpy of vaporization. Are sometimes referred to as the heat of vaporization. And really, the heat of vaporization is the energy that's required basically to do the phase transition, to take something from liquid to gas or gas back to liquid. And that does occur at the same temperature. So that occurs at the same temperature as to when that process sort of occurs. And R is our gas constant. It is the 8.314 version of it. And our T is our temperature in Kelvin. So we could use this to calculate things like vapor pressure if we know some information along the way. So let's take a look at an example here. Since we have the answer, it's going to see how we get to that answer. So we would want to use the equation that we just saw, which is the natural log of basically P at T1 over P at T2 is equal to our delta H of vaporization over R 1 over T2 minus 1 over T1. So here we do want to convert obviously our temperatures into Kelvin. So T1 would be 25 plus 273. It's going to give us 298 Kelvin. T2 would be 65 plus 273 is going to give us 338 Kelvin. P1 in this case is 23.8 torr. And let's see here. We got temperature, that. We got delta H of vaporization is 43.9 kilojoules per mole. All right, so we do have everything that we sort of need here. We could take the natural log of our P1, which was 23.8 torr. We can leave it in torr. We don't have to convert it over our P of T2. That's going to be equal 43.9 times 1,000 joules divided by 8.314 joules per Kelvin per mole. So you may be asking, why did I multiply it by 1,000? I did that because of this part of the formula here. Heat of vaporization, heat of fusion, as well as we'll see a little bit light. That's usually given in kilojoules. R is in units of joules. So you need to do some type of conversion between those two. Otherwise, you're going to be off. So what I did is I multiplied the kilojoules by 1,000 to convert it into joules. So everybody will be in the right units. So that's why I multiplied by 1,000 to get everybody into the same units. You could, if you wanted to, took the 8.314 and turned that into kilojoules, but you do have to do some type of conversion. Otherwise, you will be off. We're going to do 1 over our T2, which looks like 338 minus 1 over 298 here. And if we do some cleaning up of perhaps the right-hand side here, we got 1 divided by 338 minus 1 divided by 298. We're going to times it by 43.9 times 1,000. And then divided by 8.314 there. That's going to give us something like minus 2 natural log of 23.8 over PT2 is going to give us, looks like minus 2.0969. We need to get rid of the natural log on both sides. So you're basically going to take E of both sides on your calculator, E of that guy and E of that guy. And if you take E of the guy on the left there, that's going to give you just 23.8 over P of temperature 2. And if you take E of our minus 2.09, that's going to give us 0.1228. Almost there. So we're going to multiply the PT to the other side and divide back the 23. So we're eventually going to take 23.8 and divide it by 0.1228. And that does give us our final pressure here of 194 torr in this case. So multiply this to the other side, divide by this. And we'll end up with this. So any questions on that calculation here? Again, the main thing is temperature in kelvins and really that delta H and that R. Next semester, if you take 200B, you'll come across using those guys together in a lot of formulas. And you do want to make sure that you keep those guys in the same units. Any questions on that there? Okay. Then let's just talk about some of these processes. The that occur. So obviously boiling occurs when a liquid water is heated at high temperatures. We do start to see bubbles form of water vapor. And when it does reach the surface, they basically can escape. And that is really when, boiling does occur. Sometimes if you've heated up water really at the beginning, like if you're gonna make noodles or something like that, you heat it up. You oftentimes will see a whole bunch of little kind of bubbles ish type things. And that's really not it boiling. That's really just the solubility of CO2 in that water being less soluble and coming out really quick. It doesn't really start to boil until obviously you start to see those big bubbles basically kind of working its way to the surface there, where it obviously can escape when it reaches there. In order for those bubbles really to make it, since they are kind of filled with water vapor, they need to be at a pressure that's equal to atmospheric pressure. Otherwise, before that, they will pop before they get to the surface. If the pressure inside is obviously not equal to the atmospheric pressure in that particular case. Um, So, at what temperature something boils does depend on temperature and pressure, and we'll see a little bit of that effect a little later on as well in this chapter when we look at sort of the relationship between temperature and pressure and things like normal boiling points and stuff like that. This usually occurs obviously at the boiling point, and obviously that is the same temperature where we go from liquid to gas and gas back to liquid. Now, raising the pressure increases the boiling point. So something like a pressure cooker here, again, with that really tight lid on it, it holds the pressure of the vapor above the liquid, resulting in an increase in boiling point. So we have a lot of vapor above the liquid, and it starts to boil at a little bit higher temperature. So lowering the pressure will decrease sort of the boiling point as well. Boiling is actually a cooling process, and it may not seem that way, um, when you're doing it, because obviously there's a lot of heat involved in that process. But we do know it's actually a cooling process if you think about, if you ever remember putting a thermometer, for example, into a boiling water. And sometimes people are scared when they use their thermometer because it's like, hey, my thermometer only goes to about 100 degrees Celsius and I'm starting to boil. Is it going to run over and break my thermometer as it's heating up? And it doesn't, right? So it kind of maintains 100 degrees Celsius, probably not exactly 100 degrees Celsius, depending on where you're at. But it's actually a cooling process. So although we are heating from the bottom, as these molecules basically are going through the liquid trying to escape, they are going to basically lose a lot of energy. And obviously, the solution loses a lot of energy. But once they're able to actually escape into sort of the surroundings, they actually are moving a lot slower. And they basically lowered sort of the overall kinetic energy of the surroundings because they took a lot of energy to get themselves out of the liquid phase. They end up basically um, moving a lot slower when they hit the air. So although we're heating from the bottom, we're actually cooling from the top. And that's why, again, when we hit something like the boiling point of water, it does maintain, at 100 degrees in an ideal situation. It doesn't really go higher or lower. It will maintain at that temperature as you're boiling it. Now, when we obviously go through that process of molecules converted from liquid to gas, that is obviously the process of evaporation or vaporization. And that is an endothermic process. So we do have to put heat and energy in there. And that's what endothermic means, right? Heat and energy is absorbed. While condensation is when we go from gas back to liquid, and that's an exothermic process where heat and energy is released. And although we don't really talk too much about energy in here, we did just see it, delta H, which is again referred to as the enthalpy. It's kind of the heat of a reaction. We recognize things as being exothermic or endothermic by delta H values. If the delta H value is negative, it's an exothermic process. If you have a delta H value that's positive, it's an endothermic process. And I bring that up because in your textbook, they assume that we covered that chapter, which we used to do. We don't do that anymore. But that's, again, if you see those sort of symbols, delta H, which refers to enthalpy, if you have a negative value, again, it is exothermic. If you have a positive value, it's endothermic. It doesn't really matter the actual number. It's actually the sign that's really the important part of it. Also, as you maybe know as well, again, as I mentioned, it does occur at exactly the same temperature, that process, and that is the boiling point. So for water at 100 degrees Celsius, that is where we have really the transition occurring from liquid to gas, or gas back to liquid. And it's not until you get a little bit above 100 degrees that you kind of go into the gas phase, not until you're a little below 100 degrees that you go into the liquid phase. But dead on 100 degrees Celsius, you basically have both phases in equilibrium with each other, which means you have basically both processes occurring at the same time. You have liquid going into the gas phase, gas guys to slow down, drop back down, and go for a swim in the liquid phase at that point. So as I mentioned before, as the liquid molecules basically escape, they do take a lot of kinetic energy with them. Again, it takes a lot of energy to kind of get themselves away from their intermolecular forces and escape the liquid part into the gas. And overall, you're sort of cooling the kinetic energy, if you will, for the liquid part. And as I mentioned as well, as soon as they're able to really break away from that really strong hydrogen bonding force, they're going to enter the air where those gas molecules are moving a lot slower, and thus really lowering the overall energy of the surroundings as well. So overall, as weird as it sounds, boiling is sort of a uh, evaporation is really more of a cooling type process in that sense. As water evaporates or cools, the evaporation rate decreases, and we can maintain evaporation rate when water comes in contact with a warm surface. That is why we feel cool, right? When we start to sweat, for example, or if we get water on our hands or our body, because when we have water on our, say, hand or whatever, it's going to start picking up a lot of heat and energy, and the process of evaporation is going to start. And where does that water that's on your hand pretty much get all that energy from? It's going to get it from your actual hand. So your hand feels cold when you have obviously water on you, because you have an increased rate of evaporation that happens. That again is why we sort of sweat, right? To cool ourselves down. It's kind of a process of cooling our body down, because as we sweat, we obviously are increasing the evaporation rate and kind of cooling ourselves down. Now, condensation, again, on the other hand, is when we're going obviously from gas back to liquid. And that's going to occur as we get some of these slow moving gas molecules that no longer can escape each other. So as they kind of hit, they clink and kind of drop down into the liquid phase and go back in. And it's actually sort of a warming process in that effect, because as they're moving, they're going slower. So they drop out of the gas phase in the air. It's going to warm up the um, sort of surrounding in terms of energy. And obviously, as they start to make some more bonds and hydrogen bonding, that's also an exothermic process. Heat and energy needs to be released. As things come together to bond, energy has to be released, which is exothermic as well. So it's sort of a warming process. It's why, right, when you sort of take a shower, for example, a hot shower, you have a lot of steam in there, right? And you feel really warm because you have a lot of steam, you have a lot of gas molecules that are going through condensation. As those gas molecules go through condensation, they're throwing off all the energy in the room, and your body's there to pick it up so you feel warm. Then when you shut the shower off, right, now you have the opposite effect that we just talked about. You have a lot of water on your skin, which then increases the rate of evaporation, and you feel cold in that sense. There you go. Life lessons. These are things you need to learn, I suppose, right? So when we talk about the heat of vaporization, which is the delta H, like I said, that is strictly for the process of doing those two things, going from liquid to gas and backwards. The value to do that is the same, regardless of which way you're going. It is really the sign that's different. So, for example, for water, if we went from liquid to gas, it is positive 40.7 kilojoules per mole. which give or take is positive 2260 joules per gram. In terms of energy required, again, not to change the temperature, but simply to take liquid water at 100 degrees Celsius to gas at 100 degrees Celsius, or steam at 100 degrees Celsius. And going the opposite way, going back from gas to liquid, it's minus 40.7 kilojoules per mole, or minus 2260 joules per gram. And that is an exothermic process here. Again, our negative number indicating that as well. So as I mentioned before, your showering effect, again, a big rate of condensation happening, and that's why you typically do feel pretty warm in those situations. Any questions on that there? Okay. Another important, obviously, process is that transition really from solid to liquid and backwards, and that is obviously melting and freezing. So here we're talking about the process of going solid to liquid and liquid to solid. Also occurs at the same temperature for something like water, that's 0 degrees Celsius. That is a normal melting point or freezing point that's happening. And again, melting occurs when they do gain enough energy to basically get away from each other, the molecules, and sort of break apart. Freezing occurs obviously of the opposite effect. When they release enough energy, they no longer could really come together. Again, at 0 degrees Celsius, we have kind of both phases in effect. So if we talk about water, we essentially have sort of like ice crystals at that point. We got kind of ice and liquid water happening, just like sort of the boiling point is not really until we get a little bit above 0 degrees that we really do have liquid, or a little bit below 0 degrees that we have sort of solid occur. Now, to get water at 0 degrees to form ice, we do need to release energy, and that is going to be exothermic. And when we do need to sort of melt it, we need to put energy in. That's going to be endothermic. This also explains sort of what happens in one of the weird sort of things for water, which is the density of solid water or ice is less dense usually than liquid water here. And as you can see here, when all these water molecules come together in the solid phase, they're all doing hydrogen bonding happening. And they do create all these big spaces between the different water molecules. And again, density, right, is mass divided by volume. So we now created this bigger volume between everybody. And we do see that the density comes down. So the process of going from solid to liquid, as we'll see, and backwards, also there's energy required just to do that. And that is what's known as the heat of fusion, delta H of fusion. And the heat of fusion, for example, for water is somewhere around 333 joules per gram. And if you remember, what we just saw was our heat of vaporization for water is something like 2260 joules per gram. So the transition of going from liquid to gas, which is the heat of vaporization, takes a lot more energy than it does to go from solid to liquid. And that is because as we go from solid to liquid, everybody is still relatively close to one another. But they haven't really fully broke apart from each other. But as we do that transition of going from liquid to gas, they're going to 100% break apart from each other. So it takes a lot more energy to do that transition of going from liquid to gas than it does going obviously from solid to liquid. And the last couple of transitions is sublimation and deposition. So sublimation and deposition is the process of going from solid directly to gas, or gas directly to solid. Here we do skip the liquid phase along the way. So dry ice is an example of that. Dry ice is really CO2, carbon dioxide. And it goes directly from solid to gas, skipping the liquid cleanup in that particular situation. And we can't calculate delta H of sublimation or delta H of deposition, which is sort of the reverse process. and it would just really be all of the delta H of fusion and vaporization added together. So I'm not going to do too much in terms of the energy or anything like that. So again, as I mentioned earlier, it does take a lot more energy, as we can see here, from the molar heat of vaporization versus the molar heat of fusion. And again, up here, this is our solid to liquid transition. This is our liquid to gas transition that's happening. And you could calculate, what's happening along the way if you wanted to do sort of a transition. And again, we're not going to really do these calculations because we don't officially talk about specific heat, but you might remember specific heat from an earlier class. And it is this equation here, and that is Q, which is heat or energy. M is mass. Delta T is the change in temperature, which is our final temperature minus our initial temperature, actually in degrees Celsius, one of the few that you leave in degrees Celsius. And S is our specific heat capacity. And for example, something like liquid water, it is a number maybe you've seen before, 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. So we typically use specific heat equation if we look at, say, a heating and cooling curve, anywhere where we change the temperature, but the phase stays the same. So we would use that specific heat equation from any process, say here, where it's going, say, from minus 20 to 0, but it's all ice in that point, maybe from 0 degrees all the way up to 100 degrees. It's all liquid water at that point. You would use that equation. Going from 100 degrees and above, it's all gas at that point. You would use that equation. Now, on those places where we do the phase transition, as you can see from this curve here, before I scribbled all over it, but right about here at exactly 0 degrees, it is plateaued. And that is where the transition occurs from liquid to solid and solid to liquid. Again, not until you get a little bit above that 0 degrees that you do get liquid, and below it you do have solid. And that's where we'd actually would use our delta H of fusion in a calculation. And same thing happens up here as I scribbled all over it. We'll just make some more scribbling. I think that looks nice. And that green little plateau line there. And again, that happens right at 100 degrees Celsius there for liquid water, or for water. And that's our transition of going from liquid to gas and back to from gas to liquid. And that's where we would use the delta H of vaporization in terms of a calculation. Um, so this is a heating cooling curve as we go from solid to liquid to gas. That is all endothermic processes. You need to put heat and energy in to do that, and vice versa. If you head the opposite way, going from gas to liquid to solid, that's all exothermic processes. Everybody needs to get rid of energy along the way in that process. Any questions on that so far? So how do we know sort of the effect of pressure, temperature on what phases we would expect? There's actually something that's referred to as phase diagrams, which help us understand, sort of pressure and temperature sort of combinations that we need for things to be in certain stages. So a phase diagram will show basically the three phases of a substance, and that's solid, liquid, and gas, and the 6 interconversions that occur. So what are the 6 interconversions? Well, it is obviously melting, freezing, evaporation, condensation, sublimation, and deposition. So all those sort of phase changes is what we're talking about. And it basically is shown in sort of the temperature pressure relationships that occur. We're going to see a graph here in just a second of one. And on that graph, you will find a point that is referred to as the triple point. And at the triple point, that is sort of the temperature pressure combination where that substance will be in all 3 phases at once. So you'll have solid, liquid, and gas basically occurring at the same time. They're all in equilibrium with each other. Water, as we see, has sort of an unusual melting point line, has sort of a negative slope. And as we talked about, that's what has to do with it having sort of a lower density in the solid form than in the liquid form, which is an unusual sort of characteristic. So there's a couple other points on this curve that we'll see. One is the critical temperature, sometimes abbreviated TC, and that's basically the temperature at above where there's really no distinction between a liquid and a vapor. So there's kind of a point where you get a temperature pressure combination that the substance basically will sort of be a liquid but have a lot of gas-like properties, so that sort of flows together, and it's really a temperature pressure situation, and that's also where our critical pressure would be, that point where there's kind of no distinction between those two phases. They just sort of flow into each other. That's basically where we find what is referred to as a supercritical fluid happening, is that transition between the liquid and the gas phase at the temperature and pressure condition where there's really no sort of difference between those things. We have something that has a density of a liquid, but it will flow very much like a gas in that particular case. So let's take a look at a generic phase diagram here. And this is just a generic one. And again, this is typically what one looks like. We have pressure on the Y, we have temperature on the X, and we have our solid, liquid, and gas. And that's typically sort of where you would find these guys on most of these sort of situations. And a couple of points here, right here is the triple point. So where that point is, if I could draw a straight line, we'll imagine that's straight. If you went down at that particular temperature, and if I was able to draw a straight line going left, which is almost straight if you close your eyes, that pressure combination there is basically where we would find all three of these phases happening at once. So the thing would be both solid, liquid, and gas all pretty much occurring at once. Now, when we think about normal melting points, freezing points, boiling points, these things do occur at a standard sort of temperature and pressure. And when we talk about standard temperature and pressure for things, kind of normal temperature and pressure, usually that implies 25 degrees Celsius and 1 atmosphere. So, for example, we'll just hypothetically say this is 1 atmosphere right here. What that would mean is if I drew a straight line across, right here where it crosses the boundary between solid and liquid, that would be the normal melting point and freezing point temperature. If I went straight down, I could find that kind of normal melting and freezing point temperature by again drawing a much straighter line than I just did there. Also, when we come over here where it crosses this line at that point, that is the transition between liquid and gas, and that would be the normal boiling point for that particular substance if I went straight down as well. In addition, if we come all the way out here where we have this point, that is the critical point. That is the critical temperature and pressure at which, as you can see, the liquid phase sort of just kind of blends into the gas phase up here. And that's where we find our supercritical sort of fluid would occur. And again, that's something that has sort of a density like a liquid, but does flow like a gas. In addition, down here where we're transitioning from solid directly to gas, that is where we have sublimation and deposition occurring, obviously on the bottom here between that transition there. Now, under normal conditions, normal things, for example, if this was a normal substance, we would see that we wouldn't see it go directly from solid to gas. We would definitely have to way lower the pressure down, right? And probably also, kind of increase the or decrease the temperature as well to get that transition to occur. So if we look at something like here for carbon dioxide, this is the phase diagram for carbon dioxide, and we have our solid, our liquid, and our gas. And this is dry ice, right, is basically what this is. And again, normal pressure is about 1 atmosphere. So at normal pressure and normal temperature, which is right about here, right, we could see that at normal pressure, we go directly from solid and then jump right into the gas phase at this point. And that's again why when you lose something like dry ice, you don't get that water cleanup that you need. You obviously go directly from solid into the liquid phase. You could also see that if you wanted to force something like dry ice to actually go from solid to liquid, you would need to kind of beef up the pressure from above our 5.1 and also bring the temperature, in this range here to get it to basically go from solid to liquid. So that is a pressure. I don't know what that pressure would be, but that's 5.1 atmospheres. That's 72 and a half. So that's a lot of pressure, which is obviously not normal pressure here. So you would need an incredible amount of increase in pressure to get it to go from solid to liquid. And under normal conditions, that doesn't happen. Obviously, normal conditions is way down here, and that's why we jump from directly solid into gas with dry ice. Any questions on that there? This would be its critical point over here. This would be its triple point. So if you could get it to a pressure of about 5.1 and you could get it to a temperature of minus 56.6, you would have all three phases sort of happening at once. Any questions on that?
Yeah, Professor Efron, you said that S2P is 25 degrees Celsius and 1 atm. How do we know when to use that for standard temperature and pressure versus the 1 atm and 273 Kelvin? Because isn't 273 Kelvin 0 Celsius?
It is. So for standard temperature and pressure, it really is in terms of gases, like we were talking about, and obviously in the gas chapter, it definitely is 273 Kelvin and 1 atmosphere. Okay.
Okay.
When I say sort of standard pressure, it is what is really referred to as well as standard pressure and temperature. You could kind of think of outside of sort of gases, kind of normal pressure and temperature, and kind of normal pressure and temperature is usually 25 degrees Celsius and 1 atmosphere. And what I mean by that is when you look up, you'll see a lot of this in 200B as well. When you look up a lot of things in like tables and table type values, those things are normally done at a pressure of 1 atmosphere and kind of room temperature of like 25 degrees Celsius. So a lot of times people sometimes refer to as kind of standard sort of temperature and pressure, and not really standard temperature and pressure like in the gas sort of definition. But sometimes people say it that way because it's really a lot of what all table sort of values are is those two temperatures. So since we do have a test coming up in just a second here, definitely this is the standard temperature and pressure for today's exam. Anything dealing with gases, that's standard temperature and pressure. Outside of that, you could think of sort of standard temperature and pressure, kind of like normal, everyday sort of temperature and pressure, which is what most sort of table values are made of.
Okay, thank you very
You're
much.
welcome. Other questions on that? Okay. So let's take a look at one here and just sort of figure out real quick here, take a couple of minutes here. And for each of these sort of temperature pressure combinations based on our carbon dioxide curve here, what phases would we expect these guys to be in? So just take a minute or two and then we'll talk about it. Okay, let's take a look at this here. So really what we want to do is just kind of find where all those points are. So we got 20 degrees Celsius and 72.9. So 72.9 is that dotted line, and 20 degrees Celsius would put us, somewhere over here, I'm thinking. And that means that we are probably in the liquid phase for our first one. Um, at minus 56.7 and 5.1. So minus 56.7, which is here, and 5.1, which is right about there. That puts us right in the middle of everybody. That is the triple point. So that is where we have solid, liquid, and gas all occurring at once. If we go to 10 degrees Celsius, my picture is really small here, and 1 atmosphere, which is like here. So if we do that, 1 atmosphere until about 10 would maybe put us somewhere around in that ballpark. And that means we should be in the gas phase at that point. Remember that that's solid, liquid, and obviously over here is gas over this point. Minus 78.5 and 1 atmosphere. So 1 atmosphere and minus 78.5 is right here, I think. So I think that's right on that line. And that is right on the line between our solid and our gas, if I'm not mistaken, there. And that means that we would actually be right on that line. We have both phases in equilibrium at that point. So that should probably be solid and gas happening at that point. I'm looking at my picture right. And lastly, we have 50 degrees Celsius and 80 atmospheres. So 50 degrees Celsius is way past here, and 80 atmospheres is like way up here. So we would probably be in that supercritical fluid over here. Again, that's something that kind of has a density of a liquid but flows like a gas. Any questions on how to identify it? Just like, by the way, if you were sort of on that line between solid and liquid, you would be in both phases. So remember, right at that line, you got something in both phases. And if you're on this line, you have also something in both phases as well. Any questions on how to use a phase diagram? You need to know the phase diagram, what it looks like, where solid, liquid, gas is, where you can find your 6 conversions, your triple point, and to be able to answer questions such as this here. Any questions on that? All right. So just before we kind of quit here for today, just to touch upon the earlier question that was just asked, again, when we talk about sort of that standard pressure, temperature, and those type of things, there's actually 3 things that are sort of associated with that sort of standard table type values. And again, that's usually if it's something with a temperature, it should be 25 degrees. If it's something that involves a pressure, it should be 1 atmosphere. And if it's something that involves concentration, it should be 1 molar. So when again somebody says sort of standard conditions, table type conditions, or normal conditions, these are usually the 3 things that are sort of in play if you would have something made in a table under sort of normal conditions. Again, as we talked about a second ago, STP for gases is 273 Kelvin and 1 atmosphere. Uh, yeah. So if you're asking liquid and a gas would go, if you were like on this point here, this would be your boiling point. If you're right on that line, that would be liquid and gas. At the critical point, yeah, I guess technically right at the critical point, it's technically the end of the line, but it is still on that line. That would still be sort of something that's between a liquid and a gas at that point. You're just at that point where it's really above it. There's really no distinction between it. So at the end of the line and kind of on the line, there's some distinction. Like you could kind of tell the liquid, the gas part, But once you go above it in that sort of supercritical fluid area, there's really no distinction in terms of the phase between those two. Kind of all blends together. Other questions? Okay. So we'll stop there. I think it's probably a good stopping point. And obviously on Thursday, we will continue lecturing. Obviously, there's no lab today. The due date for the titration experiment is a week from today. So that should give you plenty of time to knock that out if you need to. Well, you need to, but it should give you plenty of time to finish it and stuff like that. We'll continue lecturing on Thursday. And then we're going to roll into, I think, maybe a gas experiment as well on Thursday. So it'll probably be experiment 11, I think. And so the exam is like normal. There'll be a multiple choice part. There will be obviously a written part where you have to show your work. And obviously anything that you need, I think, should be provided for you. You got periodic tables, some conversions, some constants. I think you even got some solubility table up there if you need. So you should have everything hopefully that you need. Remember that you need to use the proctorial. Make sure to do your best to show you your work area, what you're writing with, and that there's nothing else out, obviously, that you shouldn't be using. And make sure that you do upload it pretty much immediately after you submit it. Other than that, any questions on anything?
Will you give us the different R values?
Yeah, so you'll have the R values or whatever ones that you need.